Question 10 is the last of our derivative-oriented questions on this final exam. So we're told to find any critical points and then use the second derivatives test to determine any local extrema, or saddle points, of the function x cubed over 3 plus y squared plus 2xy minus 6x minus 3y plus 5. And any question involving extrema is always a little bit of a process because we've got to take both first and second derivatives, we've got to find the critical points as the problem suggests, and then we've got to figure out, well, how do we determine if these are local maxima, local minima, or just saddle points, which involves using the discriminant and the second derivatives test. So we'll take this step by step. The first thing we need in order to get the critical points are the first derivatives of this function. So the partial of f with respect to x, treating y as a constant, is going to be x squared. The second term differentiates away to 0, plus 2y, minus 6, and the other two terms also differentiate away to 0. And the partial of f with respect to y, now treating x as a constant, is going to be 2y plus 2x minus 3. So we've got two ways that we can get critical points. One way would be if there was an ordered pair x comma y that made either of these first order partial derivatives undefined. But because they're polynomials, we know they're defined absolutely everywhere. So we're not going to get any critical points that way. The other option is from having an ordered pair x comma y that makes these partial derivatives simultaneously equal to 0. So let's see if there's any such points. We kind of expect that there will be, or else this is going to be a pretty quick question. So we're going to set x squared plus 2y minus 6 equal to 0, and simultaneously 2y plus 2x minus 3 equal to 0. Now there's lots of ways to solve a system of equations, but given that 2y, positive 2y specifically, appears in both of these equations, one approach here might be to subtract the second equation from the first equation. So we subtract the second equation from the first equation. And what do we get? Well, we'll get x squared. The two y's cancel each other off. Minus 2x. And then minus 6 minus 3. It's going to be minus 6 plus 3, which is minus 3. And that's everything on the left-hand side. And the right-hand side is just 0 minus 0, which is 0. Now we've got a quadratic equation that should be pretty familiar to us. We can in fact factor this quadratic equation. We don't even need the quadratic formula here. That factors into x minus 3 times x plus 1. So we get two possibilities. X equals, try that again. X equals positive 3 and x equals negative 1. Now we need the full ordered pair. So what are the corresponding values of y? And there could be several. We could have a bunch of ordered pairs where x is equal to 3 and y is equal to different numbers. Or x is equal to negative 1 and y is equal to a bunch of different numbers. We need to go back to our equations and figure that out. So let's see, when x is equal to 3, if I substitute that, I'm going to sub it into the second equation, just because it's a little bit simpler, not having to square, not that it really matters in this case. So then we get 2y plus 6 minus 3 is equal to 0. And so 2y would be equal to negative 3. And so y would be equal to negative 3 over 2. So x comma y equal to 3 comma negative 3 over 2 is a critical point. When x is equal to negative 1, we get 2y minus 2 minus 3 is equal to 0. And so 2y is going to be equal to 5, and y is going to be equal to 5 over 2. So x comma y equal to negative 1 comma 5 over 2 is also a critical point. And those are the only possibilities. Those are the only ordered pairs that make both of these first-order derivatives simultaneously equal to 0. Now, just because we know they're critical points, that doesn't tell us anything about whether they're local extrema or just saddle points. And if they are local extrema, are they local maxima or are they local minima? For that, we need the second derivatives. So the partial of f, the second order partial of f purely with respect to x, that's going to be equal to 2x. The second order partial of f purely with respect to y is just 2. And we're also going to need the mixed order partial derivative. So taking either our first order partial with respect to x and then differentiating that with respect to y, or taking our first order partial with respect to y and differentiating that with respect to x. Either way, we can see that, again, we get the constant positive 2. So the discriminant then which remember is the second order partial with respect to x times the second order partial with respect to y minus the square of the mixed second order partial derivative. In general, that's going to be 2x times 2, which is 4x, minus 2 squared, which is 4. For our first critical point, for x comma y equal to 3 comma negative 3 over 2, we get that d is equal to, well, the value of y actually doesn't enter into it, so that's just 4 times 3 is 12 minus 4, that's 8. That's a positive number, so that tells us that, yes, this critical point at least is a relative extremum. Now, is it a relative maximum or a relative minimum? For that, we'll look at the second partial with respect to x. And so that's 2 times 3, that's 6. That's also positive. And so a positive discriminant with a positive second partial with respect to x. The second derivatives test tells us that that's a relative or a local minimum. What about the other one? The other critical point was negative 1 comma 5 over 2. So there the discriminant is going to be 4 times negative 1, which is negative 4, minus 4, which is negative 8. Well, that's less than 0. So that's not a relative extremum of any type. That's a saddle point. We only had the 2 critical points, and now we know how to categorize them. One is a local minimum, the other is a saddle point.